Okay. Okay. Good afternoon. Good morning.
Hello, good morning and good afternoon, everyone. We are sending our greetings from Istanbul, Turkey. I am Hande Gürsoy Haksevenler from Marmara University, Turkey, and it's a pleasure for me to be here today as a moderator of 9th Advanced Oxidation Processes School webinar to be presented by Professor Idil Arslan Alaton. These webinars are a series of events to spread knowledge about what the International PhD School on Advanced Oxidation Processes has been doing. And the International PhD School on Advanced Oxidation Processes is an initiative of academics and scientists with a strong and internationally recognized expertise in the environmental applications of AOPC. The aim of the school is to bring the members of the scientist community themselves on voluntary basis in promoting the higher education of young scientists in the research field. The school was founded in 2014 only for European Union students. Then after 2018, it became international with inclusion of partners from Latin America. The school promotes many different events such as summer school, series of webinars, opportunities for networking. It provides mobility among PhD students between different universities, which are members of AOPC schools, keeping PhD students updated about new positions, conferences, and other relevant news, and also awarding the International PhD on Advanced Oxidation Processes label to PhD students fulfilling the requirements set by the scientific community, and also providing best PhD thesis ever. On behalf of the AOPC School, I am pleased to present you our speaker, Professor Idil Arslan Alaton, who was my advisor during my master and doctoral studies, and who is the one who I admire her personality and her being a scientist. She has her bachelor degree in chemical engineering from Istanbul Technical University in 1995 and her master degree in environmental technology from Boğaziçi University in 1997. She has completed her PhD in environmental technology at Boğaziçi University in the year 2000. During her PhD studies, she was a visiting researcher at Tampere University of Technology, Finland in 1998 and at the University of Hanover, Germany in 1999. And she did her postdoctoral research at Berlin Technical University, Institute of Environmental Technology in 2000, and at the University of South Carolina, Department of Chemistry and Biochemistry in Columbia, United States of America in 2001. She is a full professor at the Environmental Engineering Department of Istanbul Technical University in Turkey since 2002. And she is a member of the Science Academy Turkey, the International Water Association, and as well as the Society and Diarists and Colorists. So it's yours, dear Professor Arslan Alaton. You are welcome to make your presentation.
Thank you, Hande, for this nice introduction. Yes, Hande was my first PhD student, and it's a pleasure to have her here as a moderator. She is working as an assistant professor at Marmara University in Istanbul. So thanks to her, and also a thank you to the Academy of Science Turkey, especially Mrs. Aslı Aydın Sancar, who is our technical supporter. She helps and assists us technically in this webinar. And also special thanks to Professor Luigi Rizzo for this opportunity to give you a webinar. Okay, so before I start, I would like to remind you that if you want to receive a certificate, if you need a certificate for attending this webinar, you can contact our moderator, Hande Gürsoy, and she's going to help you she's going to prepare a certificate for you. Okay, so let's then start the webinar. So here you see the headlines. I'm going to use the keywords when I say basic principles. I mean, especially persulfate activation, water and wastewater treatment applications. Here, the water and wastewater organic, inorganic components are important because they affect the oxidation removal efficiencies. Those which are interested in sulfate radical-based AOPs know that there are, like, in the last 10, 15 years, maybe thousands of papers in persulfate activation. And therefore, I would like to give some examples from our own work, where you can see the development, maybe on like changes in the slight changes in the subjects dealing with sulfate radical-based advanced oxidation processes. And finally, we'll have some concluding remarks and recommendations maybe. And would like to have, if appropriate, some questions from your side. So at the end of the session, we are going to have some answer question part of the webinar and ending the webinar. Okay, let's start with some general information. So we are using advanced oxidation processes to remove some problematic pollutants, refractory, hazardous. We try to fully oxidize them or partially to remove toxicity and recalcitrance. And we know that mainly hydroxyl radicals are involved in these processes, besides other reactive oxidizing agents and species. So we have conventional oxidizing agents like ozone, hydrogen peroxide that we combine with some catalysts, with sonolysis, and use some energy forms to produce these radicals. And a little bit more recently, so over the 10, 15 years at least, some sulfate radical-based AOPs, so advanced oxidation processes, have been developed, and they have attracted a lot of attention. So that a lot of studies have been published recently. Originally, these AOPs have been introduced, those involving persulfates, for soil and groundwater remediation in the late 90s, early 2000s, to overcome some technical limitations and problems of the liquid hydrogen peroxide, they have been regarded as some alternatives to the traditional hydroxyl radical-based AOPs. So some advantages have been reported if you look at the recent scientific literature for PS-initiated AOPs over hydrogen peroxide-initiated AOPs, like higher free radical formation, higher reduction potentials, but also at the same time some sensitivities to specific organic pollutants, reduced storage and transportation costs because persulfates are available in solid forms, and they are less sensitive towards reaction conditions, according to some publications, reaction conditions, pH, and wastewater composition, water composition. So here I just show you quickly how we can activate peroxydisulfate with UVC light. So we have here some homolytic cleavage of the peroxide bond, forming this reddish, yellowish shown sulfate radicals, and also hydroxyl radicals. There are different methods available to activate persulfates, starting from some UVC light, ultrasound, as we have for hydroxyl radical mediated AOPs, metal ions, metal oxides, some catalysts, ultrasound, and we can in this way oxidize pollutants to organic reaction intermediates and ultimate oxidation products that I'm going to show you later on. So persulfate is available as potassium, ammonium, and sodium. They are generated mainly by two precursors, peroxydisulfate that I'm calling PDS and peroxymonosulfate PMS. They're also abbreviated as this, like this, in papers. So PMS is a mixture of salt, contains less oxidants and more sulfate per mass of the salt, and drops the pH more drastically than PDS. And historically, so one of the first pioneering important studies is, as many others, of course, That of Chen and Chu, cited a lot in the year 2009. They explored the activation of PMS by cobalt salts, different salts, and also immobilized cobalt titania to degrade atrazine in water under different reaction conditions. And thereafter, also before, a lot of scientific efforts have been done. So sulfate radicals have a higher, theoretically, they have a higher redox potential than hydroxyl radicals at room temperature. Of course, these redox potentials change with pH. The selectivity is mentioned, which can be an advantage if you have some some micropollutants, for example, in water and wastewater, some industrial pollutants that react with sulfate radicals at higher reaction rates, so that the other components are not going to result in competitive reactions as we have for hydroxyl radicals. So depending on the type of the organic substituent and also the type of peroxide, we can have different reaction pathways and different products. We can have characteristic intermediates such as benzyl radical and biphenyl. We can have differences in dehalogenation and hydrolysis kinetics if we use persulfate instead of hydrogen peroxide. If again we compare hydroxyl radicals to sulfate radicals, there is an appreciable difference in the half-life. Sulfate radicals can be thus more selective in their reactions with some pollutant types, which will affect their overall performance in water and wastewater, considering the background matrix. They can show better performance in degrading specific contaminants in the presence of organics and inorganics. So we said PMS, that's by the way a triplet potassium salt. Potassium, you see at molar used at specific, mixed at specific molar ratios. It's also called oxone in contrast to the single potassium peroxydisulfate salts. So it can be, there are some slight differences in activation of PMS and PDS. It's more effectively PMS activated by transition metals, for example, cobalt, copper, iron, and PDS, yielding sulfate radicals due to its unsymmetrical molecular structure. And it is also more efficient than PDS in oxidizing some organics by doped nano catalysts, catalytic materials, and noble metal catalysts through an electron charge transfer mechanism. In contrast, if we just compare it with PDS, energy transfer processes like UVC photolysis, for example, they homolytically break the peroxide bond, and we have a more effective activation of PDS using energy transfer process. Because of its lower bond dissociation energy, I'm going to talk about that and mention that when we mention the UVC activation of persulfate. There are several means of activation. Generally speaking, persulfate, UVC light, metal ions and oxides, zero-valent metals, and composite materials have been used. A lot of different catalysts and photocatalysts, power ultrasound, thermal activation, and we can continue the list with electrochemical activation and others. And PS involves free radical chain reactions through oxygen peroxide bond cleavage and electron transfer reactions. So generally speaking, we can classify the pathways of PS activation as radical-induced oxidation that you see on the left-hand side above, then the high-valent metal-induced oxidation with metals involved, transition metals, for example, and electron transfer over heterogeneous photocatalysis, where also other types of radicals are formed. Then the reactions with water, we say sulfate radicals, but when we activate persulfates, we also form hydroxyl radicals, depending on the pH. When we have acidic pH values, sulfate radicals are generally speaking the dominant reactive species. At neutral pH values, we have participation of both radicals, and when we have alkaline pH values, hydroxyl radicals dominate. As you can see, I'm going to show you some related reactions in water. Hydroxyl radicals are formed, especially the higher the pH, the more important does this reaction become. And photochemical activation, So that's the most direct way, as we know from hydrogen peroxide photolysis. In the same manner, we are forming 2 moles of sulfate radicals when we photolyze peroxydisulfate. The quantum yield is unity, as for hydrogen peroxide, and UVC photolysis at 254 nanometers of PMS is shown in the final reaction equation. You see hydroxyl radicals and sulfate radicals are formed. So when we have the involvement of PMS, the reaction mechanism can change slightly. So PEDS UVC has been efficiently used compared to PMS. We have observed in the literature better removal oxidation rates and removal efficiencies, which has been attributed to the dissociation energy of PDS, which was lower than that of PMS. You see here some information is given about the dissociation bond energies and the redox potential of PDS alone as an oxidant. It is a stronger oxidant than PMS under STP conditions. Thermal activation is also possible above room temperature up to boiling points. You see here sulfate radicals are formed. Again, at alkaline pH, we have hydroxyl radical formation. At all pH values, we have involvement of hydroxyl radicals and sulfate radicals. But at all pH, these reaction rates are much slower, the conversion of sulfate to hydroxyl radicals. Then we observe also by using probe chemicals at neutral and acidic pH that sulfate radicals are the dominant oxidizing agents, active oxidants. So activation with 0 valent metals, that was also like 5-10 years ago. There was a lot of interest in 0 valent metal using 0 valent iron and aluminium and other also bimetals for activation of persulfates. Iron is preferred because of its high abundance, relatively low environmental impact. It's not a very toxic metal, and its high reactivity. So here we have some surface and also bulk phase reactions. The 0 valent metal is oxidized by peroxydisulfate, and then the ferrous iron, since there's also ferric iron, undergoes a Fenton-like reaction. That's also possible in the reaction bulk and on the surface of 0 valent iron. So we have fast oxidation of the metal from 0 to +2 to +3, and probably you expect after some time, because there is high reactivity, fast oxidation, that the reaction stops, slows down, is inhibited at the end. So we can also have activation with other metals like 0 valent aluminium, which is the most abundant element. It's very reactive, but here acidic conditions are very important. It is accelerated, the reaction is accelerated at very acidic conditions. Sulfate radicals are formed. Here you see the surface reaction. Aluminium is oxidized to aluminium ions, and sulfate radicals are formed under acidic pH values. This can be a very selective and efficient reaction under some circumstances. Okay, then we also have a lot of scavenging reactions. Peroxydisulfate, for example, of course, reacts with the sulfate radicals. If it is provided in if it's overdosed in excessive concentrations. Also excessive concentrations of iron may result in scavenging reactions, and then reactions of free radicals terminating the reaction. See here also some reaction rate coefficients. Then high valent metal induced oxidation using transition metals together with an oxidant, the peroxide. Here it's persulfate, peroxydisulfate. We have a Fenton-like reaction. It's a very fast and efficient reaction. We have almost no mass transfer limitation. It's an immediate reaction, but the drawbacks are, so we have to recycle the metal back. So we have a lot of metal discharge. A lot of metal is ionized here, you see. It's not just ionized, it is just converted to a higher oxidation state, and then it has to be recovered or recycled back. It has to be reduced to its original form, and this can be like a limitation of this process. To accelerate the to accelerate the redox cycle, to continue this oxidation reaction, this is a critical point. We need some regeneration of the catalytic activity. That's the problem of homogeneous catalytic reactions that are initiated by persulfate and transition metals. So they are kinetically very advantageous, but when it becomes to the practical applicability, we have to consider the following, that which limits their real scale application: pH adjustment, then pH readjustment. That means we have some extra chemical cost, operating cost. The metal ions are released. They have to be collected, recovered, and treated. We have some disposal costs. And then we precipitate the iron, but also the sulfate which is formed. So if there are high concentration of sulfate, that can also be a problem for, considering the environmental discharge limits. Although sulfate is not very toxic, if we have high values, high concentrations of sulfate in the water, it can be a discharge, environmental discharge problem considering the legislations, and we can have sludge management and disposal concerns. Therefore, in heterogeneous catalytic activation, we have some advantages, like we can reuse the recover and reuse the catalyst. So there are, of course, also homogeneous reactions involved, not just heterogeneous ones. We have activation of the persulfate with the metal catalyst on the catalyst surface. We can have metal ion leaching, so that in the bulk, some Fenton-like reactions occur. But here again, since this is a heterogeneous reaction, it is mainly occurring at the surface of the catalyst. It's not the heterogeneous activation is dominating over the homogeneous ones. But again, here the concern is poor regeneration of the oxidized metal species, and metal oxide catalysts to its original reduced state can cause inhibition of the catalytic activity. Then you have some heterogeneous photocatalytic activation of persulfate. That means we have heterogeneous photocatalysis in the presence of the peroxide. There are multiple benefits. So there's a lot of reactions, active oxidants involved. So in this way, by adding the PS, the PDS or PMS, the recombination of electron hole pairs is delayed. So we improve the charge separation. With the conduction band electrons, we produce extra sulfate radicals. We form superoxide radicals. Hole oxidation generates hydroxyl radicals. And a fraction of sulfate radicals reacts with water to generate hydroxyl radicals. So we have here a collective action of different oxidizing species. We enhance the reaction by having more radicals involved that enhance the oxidation, and we also extend the charge recombination. So we inhibit charge recombination. So this is the direct electron transfer. I'm talking about the same thing, the same type of activation. Here I'm showing you the reactions involved. So you see electron conduction band reactions, reactions with the electrons and holes, and ultimately we have different types of active oxidants that react with the pollutants, hydroxyl radicals, superoxide, and sulfate radicals. And to show you the same as a scheme, the same reactions, you see here activation with visible light and near UV light is possible for these semiconductors, perovskite, so there are different types of oxides available, which can be activated in this way. We have charge separation and we have some redox reactions. Then the heterogeneous photocatalytic type, which involves indirect electron transfer, because sometimes we can also combine Fenton-like catalysts with photocatalysis, so incorporated in the photocatalyst by doping or other methods. And this system combines heterogeneous Fenton-like reactions with photocatalysis in one single catalyst. So here we have really high mineralization yields, and the iron, for example, iron can be the metal, is also involved. So the iron catalyst immobilized promotes a Fenton-like reaction at the same time. And it also scavenges or combines with the conduction band electrons, the iron. In this way, iron can be recycled back, so it is reduced to its original state and continues the Fenton-like reaction. Here it's maybe seen in a clear way. So the intermediacy involvement of iron, iron is can be reduced by the conduction band electron, so an indirect electron transfer, and it is reacting with the PDS in a Fenton-like reaction. That's one effect of this indirect electron transfer. And then we also have hole oxidation and formation of the other oxidizing agents. Okay, applications in water and wastewater treatment. So there are different types of micropollutants, industrial pollutants that have been selected as model pollutants, priority organics, contaminants of emerging concern. So there are different classifications available. We have stabilizers, antioxidants, azodyes, drugs, then surfactants, X-ray contrast agents, iodinated ones, the organic iodine molecules, stimulants, and synthetic or natural hormones have been treated with persulfate activation. Here, the pH can be important, has an effect, as we have already mentioned, because it can cause a transformation of the active oxidant from sulfate radical to hydroxyl radical, so that more hydroxyl radicals are involved at alkaline pH. The alkaline activation of PDS is also possible. Sulfate radicals are formed by catalysis and hydrolysis reactions, and the reduction of peroxidized sulfate, for example, by hydroperoxide ions to sulfate radicals, which in turn can form hydroxyl radicals. The effect of organic matter is important because organic matter, which can be is measured as TOC or DOC. So if we have filtration, we measure DOC, but usually in waters and most wastewater, these values are close to each other. TOC is close to DOC. It can be in the form of natural organic matter, especially in fresh waters. And after treatment, we have different kinds of, we say, effluent organic matter, so different type and composition of organics, but these can scavenge free radical reactions. They are known to be the most efficient scavengers. So we have most inhibition and more inhibition in the presence of organics, but it depends on the nature and the physical chemical properties of that organic matter, of course. So whether it competes or not with a target pollutant, this is also important for us. And some phenol derivatives in their ionized, that means in their deprotonated form, can activate PDS and form more sulfate radicals. So this has also been an effect, a positive effect maybe, of organic matter, which when it's industrial pollutant, we also have some aromaticity and other effects of organics. But usually we have inhibition depending on the reaction conditions. Halides, we give chloride as an example, but it can also be bromide and iodide. So they come usually from the marine environment. There can be saline, saltwater intrusion, and then we also have bromide and other halides like iodide. And their reactivities with sulfate radicals is different. Their own reactivity is different. So their the formed long-lived, slow-reacting secondary radicals, their reactions with the organics can also be substantially different. For example, chloride radicals, they have very high reaction rate coefficients at acidic pH with these active oxidizing agents. They form some slowly reacting long-lived radicals and also active oxidizing agents like chlorine and hypochlorous acids. And here we have the risk of formation of more toxic halogenated intermediates that we measure as THM and HAA. And these are some intermediates that we do not want in the reaction medium, but there we have the risk of their formation. Sometimes it's halogenation, sometimes dehalogenation follows. So if we extend the oxidation, but there is the risk to have more toxic products on uncontrolled reactions, unpredicted oxidation intermediates, especially with the other halides. So this is a problem, like bromide forming bromide and causing inhibition of some free radical chain reactions. Then other oxo ions that are present, for example, alkalinity, that's what we have in water, bicarbonate and carbonate. Alkalinity can scavenge sulfate radicals and hydroxyl radicals. And if we are closer to the pKa value, we become stronger effects of the scavenging effects. We form carbonate and bicarbonate radicals. Carbonate radical effect is stronger, so we have more inhibitory reactions. But sometimes it is also useful to have these weaker oxidants, these long-lived radicals, depending again on the concept, on the composition of the wastewater. Nitrite rapidly reacts with sulfate radicals as a scavenger, and it forms some nitrophenols, so nitrogenated organics can form, which are also not desired. So we can have some intermediates instead of the hydroxylated, we can have nitrated intermediates, which are not desired. And again, depending on what organics are targeted, we can have different reactions, but to prevent formation of these undesired products, nitroaromatics, polyaromatics, and nitrite-rich waters, that's the problem of nitrite, not nitrate, we need pre-treatment before PS-based AOPs. That's encouraged or recommended, let me say. Here I'll show you a scheme where I try to compare the reaction rate coefficients, bimolecular reaction rate coefficients between for sulfate and hydroxyl radicals with some inorganic ions, positive and negatively charged. We see that they are in a similar range, but the range of hydroxyl radicals is a little bit wider than that of sulfate radicals. So sulfate radicals is a bit more, has a narrower reactivity, but the increasing order of the types of ions, they are quite similar, not very different from each other. So the reactivities of the individual inorganic ions with these active species. So applications, we said, what is important when we have applications? We have to follow collective environmental parameters. Ultimately, we want to remove them, to get rid of them. The environmental full characterization of wastewaters and water to be treated is very important. It gives us a lot of information about. We first have to know the wastewater and water, and then we have to decide what to do with it. Then we have to support, if possible, our results with acute and chronic toxicity tests, with bioassays. And the effect of organic and inorganic compounds should be investigated, if possible, in synthetic simulations of the real wastewater. Besides multi-pollutant, we should also try to follow some organic, inorganic degradation products. If this is not possible, we may support these with bioassays. Treatment conditions should be realistic. So we should try to prevent, to minimize pH adjustment and addition of extra chemicals, increasing or decreasing the temperature, to be able to calculate the correct capital and operating costs. We should also extend these cost estimations and support them with life cycle assessment. So we should also do a life cycle assessment for all the chemicals and materials used during advanced oxidation. And the possibility of integration with conventional treatment is very critical. And according to the literature, instead of using thermal activation or ultrasound, it is more realistic to use a more economic and efficient to use instead visible light near UV if possible. Another option, an alternative energy source, is the use of light-emitting diodes recently, because they have several advantages. Short warm-up time, so you can just immediately use them. They have a relatively low power consumption. They are very economic. They have a very long service life. And environmentally, of course, they are much safer than using some of the classical traditional UV light sources. But here the problem is, we have with near UV and visible, with LEDs that work in that region, we have no problems. They are routinely used. for different applications. But when it comes to UV LED, there is a problem because their integration in large scale is still has a limit because of higher costs and lower power outputs. Still, some development is necessary to have large-scale installations of LED lamps to apply them to full scale. Because here we talk about water and wastewater treatments, tertiary treated sewage, for example, where we have really high flow rates. Optimization is very critical and very case specific. PS optimization, pH optimization. Yeah, well, I also would like to show you some examples from our own work, just coinciding with, you see, 10 years from 2012 to 2022, and you can see what we did in these years, over the years. We worked with some industrial pollutants. You see the concentrations are high. And then we tried to compare UVC treatment with peroxides. And you can here realize that with increasing concentration, we have higher removal rates of phenol. Here we work at acidic pH and room temperature. And the best results were obtained. It's difficult. It's not correct to say best results. We see that approximately, if you also have a target of TOC removal, that approximately at 20-30 millimolar, which is just something expected, these high concentrations of peroxide, because we have high TOCs and high concentration of industrial pollutants. We have similar removal efficiencies, as you can see here. Then we also tried to identify some byproducts, and they were speaking for HO dominated or hydroxyl or sulfate radical dominated oxidation pathways. Of course, identification was limited to some compounds. So hydroquinone, catechol, benzoquinone, as we know, speaks for hydroxyl radical dominated oxidation pathways. For PDS UVC oxidation, we found other intermediates that were speaking for hydroxycyclohexadienol radical and phenoxyl radical initiated pathways of sulfate radical mediated oxidation. And something else, here we have bisphenol A treatment, but again at higher concentrations. You see here the TOC is relatively high. That comes from bisphenol A. And here we have hot persulfate oxidation. You see increasing the temperature and doing some kinetic analysis. We found an activation energy which was close to those found for other aromatics. And here we have inhibition of bioluminescence, inhibition using different test organisms. Here it's most of the time Vibrio fishery, but we also use some algae and some water flea. But with Daphnia magna and Pulex, we have the problem sulfate is very toxic to them. So it's also different sulfur forms. So if you want to get rid of the sulfate, stop the oxidation reaction, you are adding some chemicals, and Daphnia are very sensitive to that. Therefore, to have more correct results, considering the toxicity controls, we were choosing to work with Vibrio because of several technical reasons. And here you see some results, almost 58% toxicity, relative inhibition under these conditions. Optimized treatment conditions. The pH is that of pure water, and we have 60 degrees Celsius. Then TOC removal becomes important, and some TOC is removed because first high molecular intermediates are formed, and when they are also removed, we observe a TOC removal and a detoxification here. Several aromatic and aliphatic products have been identified. Some products were of high molecular weight, could not be identified. The toxicity, the acute toxicity first increased because of the accumulation of high molecular weight in intermediates and decreased after some time. With progress of oxidation, we have toxicity decrease and TOC removal. For another study, here we have again bisphenol A, but this time we have different peroxides. In distilled, that means pure water, and in fresh water, untreated fresh water. Therefore, we have the TOC of bisphenol A and that of the fresh water, real fresh water, we see that we have faster bisphenol A and TOC removal with hydrogen peroxide UVC this time. And the oxidation rates, the removal of TOC and bisphenol A is inhibited in the fresh water because of scavenging reactions. If you study the environmental characteristics, the DOC is the main reason, the TOC of the inhibition. Then again, same study, optimized conditions. The TOC is given, the pH is given. These are peroxide UVC processes. Here you see comparison of UVC, which is a control here, hydrogen peroxide UVC and peroxydisulfate UVC. From the inhibition changes with treatment time, with radiation time, you will realize that, of course, at the beginning, we have the same toxicity, the inhibitory effect, but for hydrogen peroxide UVC, it increases, decreases. For UVC, since there's not much going on with oxidation, we have almost the same toxicity, no toxicity change, and also no change in the other parameters. But for peroxydisulfate, we have a rapid decrease. That's also giving us the idea speculatively that there must be some other reaction intermediates involved. That must be because of different reaction pathways. So we have here almost equal performance, complete rapid bisphenol A removal and 80–70% TOC removals. So we have parallel removals. We did a YES test, that's in vitro yeast estrogen screen test that indicated that the estrogenic activity of bisphenol A was rapidly just diminishing, parallel, of course, to bisphenol A removal. And the toxicity tells us that the toxicity fluctuates, increases first and then decreases. For HPUVC, for PDS, the toxicity rapidly decreases parallel to bisphenol A removal. The common ring opening product was oxalic acid for both treatment processes in distilled water, then some benzoic acid, succinic and fumaric acid for HPUVC treatment of bisphenol A. And in fresh water, that means we have an extra TOC, we have alkalinity, the removals decreased considerably due to the scavenging effect of organic matter, and the same for both processes. But still, after treatment, after removal of bisphenol A, we have non-toxicity, no toxicity after photochemical treatment for both processes. Another study where we used zero-valent aluminium that was used to activate hydrogen peroxide and peroxydisulfate used as the persulfate to remove micropollutant iopamidol. That's an X-ray contrast medium, an organic iodinated contrast medium in tap water, raw surface water, and tertiary treated sewage effluent, real effluents. And so we studied comparatively the effects of these peroxides. More efficient, much more efficient this time was persulfate for the removal of iopamidol. You see a characterization is provided here. Important is that there is some organic matter. The other parameters, the values are relatively low. So here the critical point is the DOC. And of course, not just the concentration, but the type, the composition of TOC. DOC completely changes here. So we see the effect of persulfate and the effect of combining persulfate activating with zero-valent aluminium, how the reaction rates increase at pH 3. And what do we have here? Aluminium release. So the faster, the more efficient the oxidation, the better is, the more aluminium release we have. So, but important is here at acidic pH, yes, we have huge concentrations of aluminium, which could be very toxic, but before the toxicity test and after discharge, so we are going to discharge at neutral pH, there was no effluent aluminium in the water. So it was not at non-detectable level. So the toxicity we have does not come if we have toxicity from aluminium, which is, of course, discharged. released during the process. Okay, so the DOC and IOPA removals were dramatically inhibited in real waters and wastewaters. In wastewater, IOPA removal was not possible, so there was no removal of IOPA, but DOC removal was still significant, so it was 28%, which is not bad. For hydrogen peroxide, for PS treatments involving PS, for HP, we have 20% IOPA and also DOC removal. That speaks again for different selectivities. So IOPA is not removed, we have inhibition, but DOC is removed with persulfate. But with HP, we have removal of both the target pollutant and the background wastewater DOC. So acute toxicity fluctuated, but this toxicity, Vibrio fischeri and Pseudokirchneriella subcapitata, which is a freshwater algae, because of the water matrix. And we also did a UMU chromogenotoxicity assay. The solutions untreated, the original and untreated solutions were not genotoxic, but cytotoxic, according to the test result. Here I show you relative inhibition of the subcapitata. You see that the synthetic, the surface water, SV, is of course more toxic also at the beginning, and the toxicity does not decrease. So we have here really bad results. We have aluminium release, we have inhibition, so it is not a recommended process, and we need acidic pH values for IOPA removal. Okay, this is another study. We have reduced graphene oxide that we use for activation of PDS and PMS for the removal of bisphenol A, 2 milligrams per liter. So it was treated in distilled water. We have different water media, tertiary treated sewage effluent. You see here the DOC is given, and here we work at around neutral pH, pH 7. The catalyst concentration is low. The oxidant peroxide concentrations are quite feasible. And we have, again, good removals, high removal efficiencies of bisphenol A. We have a radical quenching test that demonstrated the dominance of sulfate radicals here. But the problem was the catalyst was seriously deactivated even after the second reuse cycle. I'm not going to show that. Here I show you the comparative results in distilled and in tertiary treated wastewater. You can see that reaction rate coefficients are indicated for bisphenol A removal. The results are slightly better, the oxidation rates for persulfate this time. And of course, in tertiary treatment, we have some inhibition, but it is not so dramatic. The problem was that we could not reuse the catalyst. So with reuse and recovery, I mean here, filtration, centrifugation, and rinsing with distilled water and just drying. That's the recovery procedure, and using again. Then would like to finally show you a more recent study. A homemade lanthanum iron oxide was used to activate peroxydisulfate. As the industrial model pollutant, we used reactive black at a higher concentration because we wanted to mimic the effluents, dye-house effluent and UV radiation. The DOC content of the reactive black solution came from the dye stuff, but we also tried different water media here. And so we added persulfate to the lanthanum oxide, ferrioxide UVC photocatalytic treatment, and we just observed a dramatic increase in the oxidation rate. We also used as the medium besides tap water, 2 different types of sewage. You see that even treated sewage can change, the composition can change, the concentrations can change. So a decrease in DOC removal was observed from tap water going to the secondary treated higher DOC sewage sample down to 5%, which was expected because here we have a high pollution load coming from the background. You see here, you can compare the photocatalytic treatment, the enhancement with persulfate here, and we have also some control experiment, UVA with PS. which has a completely different kinetic. So even UVA photolysis of PS just brings about some oxidation. Here we have optimized conditions. So interesting here is, or promising, let me say that, well, we have to work at pH 3. This is not so attractive, by the way, and we need strictly acidic pH. If you go up to 4 or 5, we have problems. So we have the slowing down of reaction rates. The color removal is shown here, and well, recycling. So you see that in the presence of persulfate, if we do some recovery and recycle, we can use the catalyst multiple times, and we have no decrease in the performance, both in terms of color and DOC removal. But if we don't have persulfate, the reaction is slow. We have accumulation of organic matter on the catalyst, and you see that especially the DOC removal, which is more difficult, is going down, and we have a very bad performance. Okay, conclusions and recommendations. So we were here comparing the, let me say, more classical hydroxyl radical-based AOP with PS initiated AOP or sulfate radical-based AOP. We see some substrate sensitivity. That's obvious when we compare these processes. And then more specific oxidants and oxidation mechanisms are involved in AOPs. According to some papers in sulfate radical-based AOPs, especially when we have heterogeneous catalysis, there is not even an involvement of free radicals. In some papers, the involvement of singlet oxygen, for example, which I have not mentioned, is also mentioned. I did not mention as an active oxidant. The use of visible light and near UV light is encouraged. It's preferred to thermal energy and sonolysis. But for some industries, thermal activation can be an option. The main challenge here is the procedure of complicated catalyst synthesis. The procedures have to be simplified. We have to find more user-friendly, economic green catalysts, more sustainable synthesis methods and catalyst materials by lowering temperature and energy and chemicals consumption, and reuse potential is very critical. Chemical energy costs are still the main limitations of persulfate-based initiated AOPs. It's still a challenge for rescale application. And it's an economic problem sometimes. The utilization efficiency of persulfate has to be followed because it's an expensive oxidant. Sulfate can be a problem because it is, we produce sulfate, so sulfate is formed. That can cause technical, economic, and environmental problems. What else? Well, accumulation of metal catalysts, hydroxide, sludge. Therefore, metal catalysts are usually not preferred, or their concentration needs to be considered, or we should shift to nitrogen doped carbonaceous, different kinds of metal-free photocatalysts. And recently, these publications have become important so that we have higher performance and less secondary pollution, more flexibility and higher chemical stability at the same time, because we have no metal leaching. Still the interactions between persulfate recommendations, okay? So immobilization methods, catalyst synthesis, interactions between persulfate catalyst and the targeted pollutant. This is still not fully understood. There is still a challenge in reactor design and modeling issues that have still not been explored fully to understand the kinetics, the process, and develop a technology. So for commercialization, we still have lots of challenges. I think I'm at the end of the seminar, and good, and we are in time. This is nice. So thank you for listening. And if you have some questions, I may try to answer.
And thank you for this wonderful presentation. There is a question from Agustin de Oliveira asking, is there an analytical method to quantify and identify PDS from PMS?
Actually, as far as I know, we did not differentiate there, and we measured. We measured PDS. There is no problem with PMS. That's something I cannot be quite 100% sure right now. I may answer that later, maybe in a mail, but probably we could not differentiate because I do not remember that we have a different method for PMS. Sorry.
We have still time, but I don't see any more questions. Is there any? If you have, you are welcome to write on chat board. Okay, there are another question from Mr. Adel. Thank you for the presentation. Is there any byproduct formation using PS persulfate and require post-treatment?
Well, sulfate formation was observed, but there was no precipitation, no sulfite formation. And when we measured sulfate in the effluent, I think the discharge limit should be, I'm talking about Turkish legislations, but there should not be different in globally. 100, if I'm not wrong, 150 or 200 milligrams per liter. And that was not a problem. No discharge problem and also no toxicity problem.
Okay, thank you. Is there any question? Okay, from Agustina Schönen. Thanks for the webinar, a lot of useful information. A question, it is, have you tried any treatment with solar radiation? As you mentioned, it is encouraged to use it instead of UV lamps.
Well, we did not use solar radiation, but near UV radiation. So that was also quite effective, not as UVC, but still a little bit slower, but efficient removal was observed for UVA, PS or PMS treatment. Even without any catalyst, surprisingly, we had good results. So when it works with UVA, it should also be possible with solar, but we did not try in our lab.
Okay, and another question from Diego Quienon. I hope I am spelling in the right way. What analytical method can be used to measure sulfate in water?
It's available in standard methods. There are precipitation methods. Gravimetric method of analysis. You can use gravimetric analysis. It's available in standard methods of the American Water and Wastewater Association, that's APHA, AWA. There are methods for sulfate, but you can also measure it, which makes also sense if you have an ion chromatograph. So you can also measure with ion chromatography. You can follow sulfate. Different instrumental methods.
Also, another question there is from Dennis Diemter. What about degradation products from the contaminant, not the sulfate?
From the contaminant? Well, it really is difficult now to give you the, well, we have yes, besides sulfate, metal release, we have lots of degradation products, phenolic, some carboxylic acids, some aromatic compounds, hydroxylated. What else did we have? So it really depends on the pollutant type, and they are different. We measured them with GCMS, sometimes with LCMS-MS, and we have different types of degradation products that we have mentioned in papers. And right now, it's difficult for me to list them, but different aromatic and aliphatic organics.
Also, the question is going on, what are your detection limits from densitometer again? What are your detection limits for these compounds? Asking is.
Well, depending on the instruments that we have used, LCMS, GCMS, we could qualify and quantify. So depending, sometimes we could only qualify these pollutants. Sometimes we could quantify. Well, we do not work at very low concentrations. Therefore, we were working with milligrams per liter, and we could measure milligrams per liter of products, I suppose. Sometimes also after concentration, pre-concentration of the pollutants, of the product.
Okay, another question there is from Tan Bin Nguyen. What is difference in attacking mechanism of hydroxyl and sulfate radical?
Well, it depends on the pollutant. Ultimately, it's again some addition reactions. Sometimes depending whether it's aliphatic or aromatic, we can have addition reactions, hydroxylation. There we can have charge transfer reactions. Well, depending on the type of pollutant, it can change. We can also have what is it called, addition, or we can have replacement reactions, different types of. So it's difficult now to, I really cannot right now list the different types of, I'm not a chemist, by the way, so we just look and try to quantify from the literature what products can form. And usually first we have addition reactions, and then we have ring opening products, and some of them are common, some are different.
Okay, one more question from Iftekhar Ahmed. How much quantity of PDS should we use if I am using 1 gram per liter photocatalyst?
1 gram per liter of photocatalyst. Well, this is really, again, a very specific question. 1 gram of titania, for example, but it depends on for example, the pollutant concentration. So if the pollutant concentration is in the ppm range, you can use, you can start with 5, 10, 20, 30 millimolar of the peroxide. But if you work in the ppb range, you're at very low concentration, you can go down just 10-fold or 50-fold. So you have to, you can work with 0.51 millimolar. So it really depends on the pH, the background matrix. It can change. But another way is to look at the oxidant equivalent, measure the COD and try to figure out, well, you can calculate the oxygen equivalent, and the equivalent oxygen is added. That can be a starting point. But we work in the molar range, like for 20 milligrams per liter of the pollutant is important, not the catalyst, actually. But when you have a reaction like an iron catalyst and an oxidant, the ratio should also be considered. When you work with ozone and peroxide, the ratio is like 1 to, they are theoretically given in the literature, 1 by 1, 1 by 5, 1 to 10. So molar ratios can be considered.
Okay, another question from Paula Triera. I'm not sure that I am reading in the right way, asking, why do change pH? What happens if pH is not readjusted?
Well, if the pH is not adjusted, so if you use some homogeneous metal catalysts, depending again on the pollutant, you may have to adjust the pH to slightly acidic values so that the metal stays soluble. But if you work with solid catalysts or just with peroxide UVC, whatever you use, PMS, hydrogen peroxide, PS, you don't even have to adjust the pH. You can work with the natural pH. If you don't have an extreme condition, extreme alkalinity, you can first try to work at natural pH, because what we have observed is that usually for peroxide UVC processes, these are most of the time not very pH sensitive in water and wastewater. So you can work at close to natural pH values.
Okay, one more question from Tan Bin Nguyen. Any method to determine concentration of generated sulfate radicals?
Okay, so there are instrumental methods available to detect the radicals, but probe chemicals are used. You know, you can just look at the related literature because they have been used a lot. Probe chemicals like secondary and tertiary alcohols, bromide, iodides. So these are good scavengers of hydroxyl radicals. They have specific reactivities with sulfate and hydroxyl radicals. And by using different probe chemicals and looking at how much inhibition is expected and is occurring, from that comparison, you can guess which radical is dominant, but none of these methods are really 100% correct. So you cannot just rely on working with probe chemicals. You can also convert these radicals to, there were a lot of methods available, to colored radicals, stable, long-lived and colored radicals. So you can also follow color formation. So different, that was a method for, I think, electron transfer reactions to detect them. Different probe chemicals can be used and some instrumental methods are recommended.
Okay, and last question, let's say, from Agustina Shannon again, talking about scavenging effect of anions. Do you know if fluoride has a negative effect?
Fluoride, we did not investigate fluoride, but bromide, iodide can have. So why not fluoride? I mean, these are all halides, but well, the fluoride is a bit different, but well, we don't have a specific experience with fluoride, but most ions, these oxo ions and also halides, they have a negative effect at acidic pH. So not necessarily at all pH values. And it is, according to the literature, we have more effects with sulfate radical-based AOPs. For hydroxy radical-based AOPs, in my personal experience is that we did not have significant inhibition effects of chloride, for example. But with bromide and iodide, we had more inhibition. So with fluoride, I did not try. I have no idea.
Okay, I do not see one more question, last question, okay, from Barbara Jimenez. Regarding the pH in the reaction, what do you think of working at a pH close to neutral using iron complex with oxalate, for example?
Well, yes, it's an option which has been also cited a lot, using some complexing agents, organic complexing agents. Yes, then you can slightly rise the pH. You can have more acceptable, more close to neutral pH values. But the problem is when you use, for example, organic chelating agents to solubilize iron, you increase the organic carbon. Okay, it's quickly degraded during oxidation. So you observe that the organic carbon is degraded, but if you add these complexes, usually in terms of pollutant, the organic matter removal, it was not very beneficial because you are dealing with a higher organic carbon. So depending on how much of the organic complexing agent you are using.
Okay, I do not see any more questions. Thank you for this wonderful presentation and your answers to these questions. And also thank you to the participants that they were with us. It was a pleasure for me to moderate this webinar with you, Professor Idil Arslan Alaton. If you want certificates, we can get in contact it was mentioned, but my mail address is hande.fursoy@marmara.edu.tr. Thank you. Hope to see you in the next webinar.
Yes, thanks a lot, Hande, and also to the audience. Sorry for not fully answering your questions because I did not remember some of the issues. Sometimes we did not test, so I tried to answer your questions. It really, it is depending on the concept. Therefore, you have to be careful with optimization, and characterization of wastewater is very critical. Here you see the email of Professor Gürsoy Haksevenler again. Okay, then thank you for listening, for your attention. I hope it was useful for you, and have a nice week, afternoon or evening. Okay, then
Okay.
I think here we can say bye-bye and take care of you.